Okay, we're going to continue. Think again. This discussion is basically the same exact lecture as last time. Okay, it's part 2 of the previous lecture, and now we're just splitting it up arbitrarily here at this definition for ring. So here's our definition, which you will definitely want, because without this definition, the entire lecture will be very not fun to listen to. The set of all linear combinations, of the row vectors of the row vectors is called the row space. Row space of A, and is denoted as simply row A. What are the two main spaces that we talked about before in the previous lecture? The null space and column space. Okay, so we just added another guy to the mix. Okay, row A, and he's actually going to behave extremely similarly to column space. When you really think about it, there's really only one difference that separates the row A from the col A, and that is simply, instead of doing combinations of your columns, now we'll just do linear combinations of the rows. Oh. Yeah. I'm glad it already makes sense. Okay, so a few things, right? So if A is an m by n matrix, then we know that row A. Remember when we did all those subspace proofs? Yeah. It's kind of tedious, and we talked about the column A is a subspace, the null space is a subspace. I'm not going to go through all of that again, but row A is a subspace. Can you figure out which one? Is it going to be of Rm or is it going to be of Rn? What do you think? Yn.
Because it's a row.
Yeah, the whole row, how many entries are in that entire row? Well, basically the number of columns. So it'll be a subspace of Rn. And then the other, this is going to be really nice, is that the row A. Okay, really think about this. If I have just linear combinations of my rows across instead of linear combinations of my columns down, there's a fancy little operation that essentially flip-flops your rows and columns. We call that transpose. So, I mean, this isn't really actually a new concept. I'm basically transposing A and then doing a column space of that transposed version, because those would just correspond to precisely what would have been the rows before. So the column space of not the regular matrix, but if I transposed it and made those rows and columns flip-flop spaces, definitionally now we're talking about the same exact linear combinations. Okay, so that's kind of a key thing to note. Even though we've introduced a new definition, it's really essentially reframing this so that I don't have to write column space of the transpose every single time. I can just do row A. Yes.
So just a question on the way you wrote the sentence for the idea of writing proofs. So if you said A is Mn, which that sentence is logically equivalent to row A subspace of Rn, how can that be logically equivalent? How can you use that sentence?
This in English you can think of as if and only if.
Oh.
Whenever you read a math definition and it uses if, it's an implied if and only if. So it goes both ways. To state that M is M by N implies that its row space is a subspace of Rn.
Okay.
But if I were to start over here and state that the row space of some matrix is subspace of Rn, that tells me, okay, well then the dimensions are forced to be some M by definitely N, because otherwise that's impossible. So that's why, think of it literally, it's a double arrow because it points in both directions. You should be able to write both separately, and they would both be true. This isn't a logic, I'm just writing this as equation because that's definition. Good question though. Okay, so here's an example. In case your intuition hasn't already filled in precisely what we mean by a row. 1, 2, 4, -1, 3, 7, 0, 0, 1, and 2, 4, 6. Okay, just arbitrary numbers. The values don't really matter for the example. It's just, this is telling me, it implies that my row vector R1 is equal to, and now notation is going to matter. So as you notate this in your notes, it matters how we do this. Because these aren't column vectors anymore. We're going across a row. And if I want to really communicate that I'm talking about the row and not a column, excuse me, I use parentheses. So it's going to be 1 minus 102, like that. Okay, so I skim across the first row, and instead of writing this as like that vertical typical column vector, I'm deliberately using this notation to indicate to the person, hey, this is a row of a matrix. I've sliced across. So what would be R2? R2 would go across the second row. So 2, 3, 0, 4. And then R3,
4, 7, 6.
7, 1, 6. Okay. So, what do I mean by the row space of A? Well, the row space of this particular matrix A is, okay, everybody, look up here and read with. Now, the set of all linear combinations of row vectors is called the row space of A. Okay.
And is the node row A.
So, the row A is what?
The set of all linear combinations is the row by row.
Okay, have we articulated the row vectors?
Yes.
Okay, fantastic. What do we know? What's the shorthand way of describing all linear combinations of span? Okay, so it's the span of which vectors?
R1, R2, R3.
There we go. R1, R2, R3. Okay, bingo. That's it. Now, if I had done the transpose of A, this isn't in my notes, but we might as well do it, right? If I had taken the transpose of A transpose is equal to what?
1, negative 1, 0, 2.
Yeah, so every single row becomes a column. So the first row here, 1 minus 1, 0, 2, is now the first column. This row is now a column. What's the second column? 2, 3, 0, 4. What is the third column?
4, 7, 1, 6.
4, 7, 1, 6. So, if I were to take the column space of AT, then what am I doing? Well, so every single one of these, I'm just taking all the linear combinations of these. So the only difference here is in notation. My A1, notice I'm using the A for column instead of R for row, and I would denote it with the actual column vector. And A2 is, oops, 2, 3, 0, 4. And the third column is 4, 7, 1, 6. So then my column space is definitionally the span, all linear combinations of my columns. So you can see how we're talking about the same stuff, okay? So whether you choose to use the perspective here with row and just go across the rows, or if you're doing a problem, you're like, I just want to take the transpose and deal with this as if it's a column space because I know how to handle that, then by all means do that because it is entirely valid, okay? Does that make sense? Going between the two, whether you choose this perspective or this perspective, they are entirely equivalent. So it makes zero difference which one you choose, so long as you're careful with how you rewrite it, okay? So it's a little bit of freedom with that. Actually, yeah, I'll write this under here, So here's a little theorem. And this theorem I'm going to write down just so that you know it's basically the reason why the upcoming procedure actually checks out, okay? Because I'll give you a procedure for checking all of the different spaces that we have, the null space, column space, row space in this summary. If A is row equivalent to some matrix B, then the row space of A is the same thing as the row space of B. Gee, why might such a theorem be really, really practical if we're trying to solve certain types of problems? Well, because we didn't specify what B had to be. So, in it, general matrices versus an echelon form, that could be really easy to read. So if a row space of an echelon form, let's do that. If B is in echelon form, notice that we're not requiring what? Reduced. It just needs to be an echelon form, which is even nicer. The non-zero, meaning like all the entries shouldn't just be shut out to 0, rows of B form a basis. Basis for the row space of, we can think of it as the original matrix, but the only reason, I mean, that's really just, the implied in parentheses here is because row A is equal to what? Row B. Okay, so this is what we're taking advantage of. The fact that row B will always be the same thing as row A. So if B is my echelon form, I'll be talking about B because it's easier, but the consequences still apply back to A, even without having to do all the crazy work. So, procedure-wise, yes. Actually, let me give an example, visualize it. So let's make a generic matrix that's in echelon form. So like if I have some B, and maybe I've got like, there's 1, 0, 0, 0, 0, something, 0, 0, 0, 0, something, 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 1, 0, 0, 0, something, something, 1, 0, 0, something, 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 0, something, 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 0, 1. Okay? So this is in echelon form. You'll notice, and I intentionally included a free variable here in this column to show you that it doesn't have to be squared, okay? So that's intentional, that wasn't a typo, even though I make a lot of those, as you already know. I meant to not have it just perfectly staggered. But is it still in echelon form? Yeah. Okay, is this necessarily row-reduced echelon form? No, because I haven't put zeros above everything else. But why might it be true? Think about what the row space is doing. If I now slice out all these rows and think about them coming this way, then the span, this is impossible to just be some sort of scalar multiple of the second row. Like, when you really think about it, what you're doing when you're putting a matrix into echelon form is you're visually making it impossible. You're finding the combinations of these vectors where they are linearly independent from each other, right? So the process of putting something into echelon form is the very process of making your rows linearly independent from each other. And by so doing, you have now induced some sort of a span, and because it's span that is linearly independent, that's just what we mean by basis. Okay, so if this theorem ever seems to be like, how can we really know that for sure? Just envision an echelon form in general, and really think. If there's all zeros here, there's no way for me to scale this to generate material that exists in another variable, right? If I have no mention of any x1s in this row, how on earth would I take a combination of this to spit out something with x1 in it if there's no x1s to scale, okay? So echelon forms are convenient because they will give us, kind of just by the way that they're designed, to be linearly independent as rows. Not necessarily as columns, right? That was a whole different discussion that we've been having with the column space. But if we're taking that specific row perspective now, it checks out for the echelon forms. So, as all things do, all roads lead to Rome. All roads lead to echelon forms. You gotta go be able to do row reduction to echelon forms for just about every procedure in chapter 4, because somehow, some way, that insight of what the echelon form does and looks like makes everything really easy. And you can simplify tons of different types of problems just knowing and being familiar with echelon forms and how they relate to the definitions. So let me take a look. Let me give you the procedure. It's basically just instructions for how to practically go about different problem types. Because if you follow all the steps, you will always be able to get the desired output here. So our procedure is for finding bases. So here's the task. I want to find the basis for any of my given like special spaces here, right? So the row space, the column space, and what's the last one?
Null space.
Null space. Okay. So what's nice about it is their procedures for all three of these things kind of overlap. And so I organized in my notes a way to present it so that you can kind of like mentally flowchart the most efficient way to get through these different things. And say if you're given a problem where you need to find all three of them, okay, well then, lo and behold, doing it in a specific order is going to be the most point-and-shoot, direct, efficient way to do it, okay? So, first things first, we'll consider row space and column space first. They obviously have a close relationship, as we already saw, through transpose. So, for the row space and the column space, you are always going to begin with row reduction. So row reduce your starting matrix to an echelon form. And is a humongous word in this statement. I think people don't realize how grammatically nitpicky math gets. Imagine if I had put V. Okay, that seems like I'm specifying some specific type of form. Nope, it can just be an echelon form. So if you reduce A and you achieve something that is echelon, use it, okay? So you don't need any other specifications. That's what's nice about this procedure. Just an echelon form. And then once you're in that echelon form, so once in echelon form, now we split off. There's two different things. One thing we'll do for the row A, and one thing we'll do for the column A. So they both have in common getting to an echelon form, but here's where they diverge and how we deal with that. So take the non-zero rows. Take the non-zero rows to form a basis for my row space. That's kind of what we just stated over on the other whiteboard there. Okay? So if I'm trying to get a procedure for like figuring out what the row space is, not difficult whatsoever. Just get to some echelon form and then identify all the non-zero rows. Bingo. All those vectors will definitionally already set up a basis for you, and you just have to list them out. Did I see hand earlier, or am I just tripping? Okay. Oh, yes. Question?
No.
Oh, okay. Don't worry. I understand. The wind kept me up last night. Identify the pivot columns. Okay, yeah, so if this is for row A, now we're going to talk about the column space. So we're going to identify the pivot columns. And this is a little bit of review because we did talk about this quite a bit. Pivot columns of the echelon form. To determine their location. In the matrix. In the matrix, respectively. Yes, this is just a review statement. Now that I'm thinking about this, really think for a second. What did I spend probably 20 minutes of your time yapping about and making sure we really understood when it came to the pivot columns of the echelon form?
It's not the actual basis.
Say that louder for everybody.
It's not the actual basis.
My goodness, Sam Patchen, what is it? If it's not the actual basis, where is the basis?
It corresponds to the same rows in your original matrix. That is the basis.
Yeah.
Yeah, everyone understand that? Okay, that's all this is saying. Okay, so this is English. English is just a terrible language. Okay, so if I come over to this echelon form, then my pivot columns. This is a pivot column. Is this one a pivot column?
No.
Oh, why? Because it's good. And then here's a pivot column, pivot column, pivot column, pivot column. So then, are those the actual columns that form the basis?
No.
Oh.
I would take those relative positions, go back to whatever A this came from. Those are the columns, okay? So boom, this is not a difficult algorithm. Like, really think about it for a second.
I'm thinking about it.
To generate bases for, because it seems like a ooh, right? Find a basis for a column space. Oh, college math. No, you are straight up doing effective. When you really think about it, it's also kind of crazy, because we learned how to do these echelon forms all the way back, and our original motivation was just solve a system of linear equations, like super innocent Mickey Mouse. Dora was still fun to watch. All of the things, okay? It still is. So even the procedure for trying to solve a system of equations is suddenly spitting out bases of row spaces and column spaces. That's kind of cool, okay? There's a lot of different perspectives. So does this make sense? If you were asked to find the basis for a row space or a column space, no intimidation, okay? You think, just get it to an echelon form because I already know how to do that since the first week of class. And then know the key observation. The moment you know the key observation, it's over. There's really nothing past that you need to do. You don't even have to compute anything. It's literally copy-paste the non-zero stuff. Okay, so you don't even have to worry about if there's a specific technique of selection. No, it's use your eyeballs. Is it all zeros? If the answer is no, put it in your bases. Okay, and then for this one, it's the same exact thing. Identify which ones are the pivot columns. Are those in the echelon form the actual things to use? No. Take the positions, copy paste from the original matrix, done. Okay, so a problem like this should only take as long as it takes you to do the echelon form. Like, really think about it. If you're asked to find a basis for a row space or a column space, that only should take as long as it takes to get to the echelon form. Because the moment you have the echelon form, the problem is effectively over procedure-wise. Okay. Now the stinker is the null space. So for the null space, now I know this is going to come as an insane surprise to you. What do you think we might be doing to A? Row reducing it again. Oh my goodness.
Wow. Great.
There comes a point when it's like watching like the Marvel franchise. You're like, oh, they did it again. Okay, so row reduce A. Now the only difference, okay, so you might be thinking to yourself, if I'm just row reducing, why wouldn't I classify it under the first step here? Why doesn't that fall under this tree? Well, because now null A is a little pickier with its food, okay? We can't just take any echelon form. Any echelon form isn't going to do. We need the row reduced echelon form, okay? So reduced echelon form. That is the key difference right here, right now. This is why you're paying tuition for someone to teach you the example instead of gaslight you into thinking you understand it, okay? The difference between bases for row spaces and column spaces from the null spaces that we require for null spaces reduced echelon form. All because of what null space definitionally cares about. It cares about solutions to the homogeneous equation, right? Ergo, we want to be able to immediately express our basic variables in terms of the free variables to know how many vectors are even going to span my null space, okay? So reduced echelon form. And then we can then identify pretty easily to identify what are we actually looking for by doing this? Well, we're looking for our free variables. Because the number, remember from last lecture, the quantity of free variables for the ax equals 0 is precisely how many vectors you should anticipate spanning your null space, right? Again, that's not really, you don't calculate anything, it's quite literally just count up how many free variables exist. And that is, in fact, how many vectors will span your null space. So free variables. And find the vectors. Find the vectors that span the solution set. That span the solution set. These are the vectors that span the null space. So these vectors form a basis for the null space. So there you have it. You can find a basis for any of our given special spaces, basically entirely through just row reduction. Everything comes down to row reduction. So if you can do that one skill, boom, half of chapter 4 kind of falls in your lap, okay? Do we know exactly what I mean procedurally with this, taking the free variables and converting that count of free variables into those vectors, or should we cover that one more time? I'm going to cover it one more time.
Let's go.
We happy with this? Our general echelon form, okay? So that's how that works. Now let's talk about homogeneous real fast. It's a good review of chapter 1 because, I mean, the final in this class is cumulative back to section 1.1, so. Is it scary? I mean, considering half of the last lectures have been all about the 1.2 procedure, I think we're fine. So, if I have reduced something to a row reduced echelon form, so let's just make something up here. If it's row reduced echelon form, the only value that should be appearing in the matrix is the value 1, right? Because everything else should be zeroed out. So I have some 1, 0, 0, 0, 0. Ooh, I'll do this. 1, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0. And then I'm augmenting it because this is the matrix equation with the 0 vector. 0, 0, 0, 0. Okay, so are we clear that I'm trying to distinguish between what the actual matrix is versus the augment with the solution, right? Okay, so straight away, what do we kind of observe? It's going to be a lot of free variables. And actually, this is way too boring because I put a bunch of zeros there, so let's put something fun in here.
Fraction.
Put something fun. Actually, I think this one kind of fun.
I swear.
Let's put 2, 3, and 4 because my capacity to be creative right now is entirely 0. Okay. Now, if I'm describing the solution set here, I have x1 plus, let's see, that's 3 or 2 times x3 is equal to 0. I have that x2 plus 3x3 plus 4x4 is equal to 0. And then I have x3 and x4 be bumming, okay? These are free. Because there's no pivots for them. So they're floating around doing whatever they want. Okay, so now if I write and express the solution vector x, so x1, x2, x3, x4, by the way, I'm going to be very, very upfront. If you cannot do what I'm about to do as a decomposition, then it's going to be a rough exam, okay? Just a rough experience, okay? So, what goes in the x1 spot?
Minus 2x.
Yeah, I need to isolate it, and so it would be minus 2x3. Okay, what goes in the x2 spot? What goes in the x3 spot? He's chilling, he's happy. He is unbothered. What about x4? It's that one, like, freeloader. Okay, just a chill guy.
I'm a real chill guy.
Thank you, Chloe, for that. I needed the inspiration from Chill Guy for that. Okay, this marker
Can you do the
is
Chill Guy
not a
pose?
chill guy though, and is dead. Okay, what down?
We can separate it into x3 and x4.
Yeah, this is really two vectors, right? Because we have two. So
x3.
let's do an x3 vector. So which ones go with x3?
Negative 3.
Very good.
Plus.
And then what about my x4s?
0, -4, 0, 1.
That was really good. Okay. Now, we haven't proven this theorem in class, but that's fine. You could prove it if you wanted to on your own time. That these vectors that always kind of get factored out, the resulting thing after you factor out your free variables, they are always going to be linearly independent from each other. Okay? And since you're guaranteed to have linearly independent vectors from each other that, span every single possible solution, linearly independent, span, we're saying basis all over again for the 7,000th time in like a week, okay? So it's a basis for what? The null space, okay? Because every single combination of these two vectors are going to spit out 0 if I multiply it, okay? So no matter what I choose for x3 and x4, it's going to spit out something that is in the null space because it sends it to just 0, okay? So this is what I mean by whenever I talk about like decomposing a vector expression by its free variables. This is precisely all I'm talking about. Is this difficult to do? No. The hardest part about it is actually, ironically, just reducing the thing so that you can express your solutions like this. The key thing that I'm noticing with mistakes is you'll do this correctly, but then you'll forget to give yourself the mental space to like write this out, okay? Help yourself out and don't skip from here to here, because that is a little harder to do compared to saying this and then going to here, okay? So, okay. Does the procedure for the row space make sense? If we are doing either a row space or a column space, what is the first step always gonna be? To which form? And. Does it matter which one for the row space and the column space? No. Okay? Now if I specifically have my echelon form, but I want the row space spaces, what am I looking for? Prem, say it louder for everybody. Non-zero rows. So I go through my list of rows, and so long as it's not all zeroed out, I use it. Make sense? What about the column space? What am I looking for?
Pivot columns.
Pivot columns. Do I take the actual pivot column from the echelon form?
No.
Why do I care about the echelon form though?
So you can figure out where they are in the actual.
Yes, go back to the original one, you know the position. Okay? How far do you have to reduce your matrix if you're interested in the null space? All the way down to a row reduced echelon form. Because once you get it here, the solution spells itself out in bright neon green letters for you, okay? So this entire procedure, we're fine, we're cool, yeah? Because this is kind of a big part of this section. Okay, just a warning is that the linear, if you do row operations, you can change the linear dependence relations between your rows. Okay, this is something we haven't had to really worry about because we've only been doing the column perspective thus far. So when you're doing your row reduction, you obviously aren't changing the dependency between your columns because otherwise the entirety of like the invertible matrix theorem just disintegrates. Okay, so we don't have to worry about that. But notice I could start with a matrix A that has its rows dependent upon each other. So the original matrix could have linearly dependent rows, but after getting it to an echelon form, you could find out, oh, in fact, no, those two rows are now linearly independent from each other. So what we don't want to do is just a simple like algebraic warning. Do not conflate the linearly independent or dependence relations of the original matrix onto the echelon form, okay? So what you can't do is inspect from the original matrix and make a guess. don't try that because it's not going to work. And there is no pattern or rule that corresponds between the dependence relations of your rows from the original matrix to the row reduced. Okay? Save you the heartache there if you try to shortcut that. Okay, let's get to the next definition, and then we can add on to our lovely invertible matrix theorem, which you definitely did not short-term memory study for on the exam, and you still remember all 12 parts that you memorized, right?
Well,
Was it 4?
12 no. It's 12 What do you say?
Alrighty, here's our definition. So what's nice about this definition is we don't need to learn any new concepts, okay? It's just making more dishes with the same ingredients. This word has a very, very near and dear place to Mr. Thanacle's heart, rank.
That's crazy.
Is the dimension of the column space. So put in just math terms, the rank is the dimension of the column space. Okay? Do you see why I really prefer to think of 4.5 and 4.6 as exactly the same lecture? Okay? Because you do not want to pretend like we just forgot all of our notes on dimension. Okay? As a means of review. Dimension is simply just how many vectors do you require to actually span your space. In other words, how many vectors are in your basis. So if I've got a basis, count up how many things are in your basis. That's what we mean by dimension. So when we're talking about the rank, what we're saying is, all right, well, we obviously have the column space pretty much down pat. And now I can figure out, I have a procedure now that tells me exactly how many vectors are going to be in the basis for the column space. So the rank really shouldn't be all too big of a stretch of imagination. You're just going to do your procedure to get the column space, and then that procedure itself spits out exactly how many vectors you require to make that basis. And, well, let's just call that exact amount the rank, because that's precisely what we're talking about here. Okay? Just think of this as how many vectors are in the basis for the column space. Yes? The rank is saying how many columns or how many vectors are in the column space, the basis. Okay? So do your procedure for column space A, get a basis for it, count them up, and then you've got the rank. Another way to think about that, when you do that practically with the column space and you count those up, it ends up being just how many pivot columns. So to actually figure out the rank, you don't even need to know and identify the original vectors. You could just see how many pivot columns you have. So if you look at an echelon form, actually, this is technically an echelon form without the augment. So let's use this as an example. Is this an echelon form? Yeah, it's an echelon form. Okay. Well, how many pivot columns do I have? Do I need to know what the original matrix was to tell you exactly how many basis vectors there are? No. How many are there going to be? Ergo, the quantity of basis vectors is the dimension, so the rank is 2. Does that make sense? Okay. Here's just because I mean, you're all enrolled in the 300 level math class, so you're kind of definitionally nerds. So I'll show you this, but we're not going to use this term in the class. The dimension of the null space is sometimes called nullity. Who read the textbook? Woo. That's amazing. The nullity.
What? Textbooks are yellow.
Okay, I'm going to put in parentheses that we're not going to use it in this class so that you don't freak out when memorizing your definitions. Okay, so not used in this class. So if you, I'm just saying, wow, that's a terrible way to write that. There we go. But if you are searching up help on the internet and you see the people on Mathcora using nullity, like what on earth is that? I paid for a class and they didn't teach me that. There you go. Okay, they're just referring to how many vectors you require there to be to get the basis of a null space. Which, fun story, the nullity is literally just how many free variables are in the system. That's it. All is the same. So it's like, what's the nullity of this one? Why is it 2? 2 free variables. Okay, wow. Profound. Okay, this theorem is actually one of my favorites because it's super cool.
And it's cute.
It's super cool and it's adorable.
Is it cute though?
I don't know about you. This might not be a very relatable experience, but there are some equations or theorems in math that they're genuinely like cute, like a puppy is cute. You don't have an empirical way to tell somebody why a puppy is cute. In the same sense, I cannot tell you why this theorem is cute. It just did.
It is cute.
It is adorable. Okay, it's called the rank theorem.
Sounds kind of cute.
It's adorable. The rank theorem. Not rank.
34 lines. 34 examples.
Okay, so the dimensions. The dimensions of the column space. Of the column space and the row space. And the row space of an n by n matrix. N by n matrix A, they are equal. You might be wondering, how could I possibly know that intuitively? I don't know, maybe from the fact that the very definition of the row space could be expressed as a column space, right? And then this common dimension, okay? So this common, you can think of it as shared dimension, which we have now defined on this board as the rank. The rank of A also equals the number of pivot positions. And we just talked about that. The number of pivot positions in A. And satisfies the equation. Satisfies the equation, and this is the part that makes it cute. Okay, ready? The rank of my matrix added to the dimension of the null space is just n. And if you don't see the parallelism yet, what is rank defined as? The dimension of column space. The column space and the row space, or the null space, they're related somehow. So when we initially defined these two things, there was no apparent relationship between these two random things, okay? But now, through rank, what rank lets us do is it lets us talk about both the row space and the column space at the same time, dimension-wise. And then, but really the parallelism is happening here. The total amount of dimensions for your column space and the total amount of dimension for your row space, or the null space, just gets you the number of columns in the matrix, okay? So, this is in math form, so this doesn't look super cute just yet. I'm gonna change your mind real fast, okay? So really think about this. Rank A is the dimension of the column space of A, which is also the same thing as the dimension of the row of A, which is the number of pivot columns of A. Yes?
Yes.
Okay. Now, also think about this. The dimension of the null space is, like we just talked about, the quantity of free variables there are. So how many free variables if AX equals 0 vector, which is the same quantity, we're effectively just asking how many non-pivot columns of the original matrix. The rank is the number of pivot columns. Yes?
Yes.
The dimension of the null space is the number of non-pivot columns. Yes?
Yeah.
Well, gee, I would sure hope that if I had a matrix, that the number of pivot columns added to the non-pivot columns is in fact just all the columns, yeah? And if I have an n by n matrix, gee, what does the n by n tell me about the number of columns? It's n. Okay, that's pretty cute, I'm not gonna lie. So what this theorem is telling us is something that children can understand. It's that you take your pivots and the not pivots, and in sum total, that's just your all of the columns. Ta-da! All of that worked just for that. Okay, but do you see how these kinds of observations make equations like this have a lot more meaning to it? See? So, even further, the reason why we have this rank and everything is because now we have a way to actually relate our null spaces and our column spaces, which previously didn't have any type of relationship to each other. Okay? Computationally, they're unrelated. The way their procedure is kind of unrelated. But ultimately, the things that they are describing are inherently related by how many columns there are in a matrix. Okay? So, we'll add on a few things to the invertible matrix theorem. So, additions. These are, I'm going to put invertible matrix theorem continued because I don't need to reproduce the whole preamble. The preamble is assumed from when you first memorized it, so that preamble is still the same. A through L is all the same, so we'll now just continue on.
That's a question.
So M, because M, A, B, C, D, E, F, G, H, I, J, K, L, M, yeah, M is that the columns of my matrix form a basis of Rn. So that we covered that in the definition a second ago. N, the column space of A, is itself Rn. Because if this is invertible matrix theorem, we're assuming that A is invertible, and so all of the things are going to happen. This is going to just span Rn. For O, the dimension of the column space should be N. If the column space itself is spitting out Rn, we require n basis vectors, right? And if you require n basis vectors, that's literally the answer to the question of this. So the number of basis vectors, dimension column A, is just n. So that's easy to memorize. And then P, the rank of A is also n. But gee, wow, that's really hard to memorize considering I copy and pasted the definition and just stating that the thing that is itself is also n. Okay? So not a ton to memorize here. Q, the null space, is only the zero vector. This is quite literally saying if my invertible matrix has only the trivial solution, right, for Ax equals 0, that's what this is saying. The only solution, the only thing that will get me to 0 is itself the zero vector. Only the trivial solution. So this is a restatement with the null space language. And then our last addition, R, is going to be that the dimension of the null space is, well, gee, by definition, the zero null space, right, is just 0. So is this 6 more things to tack on to the invertible matrix theorem? Yes. But is it really new? No, not really. I mean, rank A being n is, I think, really funny, just because it is just quite literally copying and pasting O, and instead of using the dimension perspective, you're using just the rank.
It's like E, whatever the columns span.
Yeah.
And so they're basically the same.
And then O is kind of funny because n is basically saying they're giving away the answer to how many vectors you need to span it. Oh, it's right there. So, ergo bing, and then if it's invertible, then you can only have the trivial solution. So, how many solutions do I put in there? Just the trivial solution. So then it's 0. Okay. Alrighty. Is this starting to finally click? What the column spaces, what the null spaces. Okay. So this is just a lecture. So if it's not 100% clicking, do problems with it. Remember these procedures. You'll be fine. Okay.
I'll try to be fine.